these two problems don't appear to be that similar. Here I'm multiplying some stuff. I've got an exponential term. Here I'm dividing some stuff. Here it's bigger than 0. Here it's equal to 0. But actually, part of developing your mathematical intuition is being able to look below the surface appearance. Yeah, they appear different on the surface, but they have a part of their structure is the same in a very important way. On the left, it's not actually important what it is you're multiplying, because the important part for a bunch of things multiplied equaling 0 is just the fact that when you're multiplying things that equal 0, you can conclude that whatever they are, either this one must be 0 or that one must be 0. And you've learned that one in the past. That's called the zero product property. So that's part of being able to look below the surface. You could write some real complicated expressions here, but as long as you recognize, oh, it's just things being multiplied equal to 0, that gives you an entry into the problem. You know that it's not possible for 2 to the x to be equal to 0. So this part of the equation doesn't actually affect the solutions. And here we've just got that x is equal to 2. All right, so how is that related to this side? Well, if I need this entire expression to be positive, then that means that both the numerator and the denominator have to be positive, or they both have to be negative, because a negative number divided by a negative number equals a positive number. So that leads to two possible ways of thinking about the solution. Either the numerator is positive, x is bigger than 5, and also the whole denominator is positive, so that would give us that 3x plus 1 is bigger than 0, and also, x plus 5 is bigger than 0 would be the numerator being positive. And then in the denominator positive, either both of these are positive or both of those are negative. So this is true and x minus 4 is bigger than 0, or 3x plus 1 is less than 0 and x minus 4 is less than 0. So as long as all of those things are true, you know that you'll have a positive number for a positive number. The whole thing will be positive. For a negative number, you'd have, for the numerator and the denominator both being negative, you'd have to have that x plus 5 is less than 0, and also exactly one of those two being negative. So 3x plus 1 being negative. So either this or x plus 5 is negative and x minus 4 is negative. So I think that covers all the possible cases. But all of these details aside, that's not really the important thing. The important thing is noticing that if you know that this entire expression is positive, then that lets you write out all of the possible combinations of being positive and negative for each of the terms that would make that happen. And you can think of each of these terms being multiplied or divided as a single blob whose result is either a positive number or a negative number. And it doesn't matter what positive number or what negative number. It just matters whether or not the term itself is positive or negative. So you can apply that same kind of reasoning in a lot of different situations. So let's say I've got this cubic equation, and I want to know, is f of 1,000 bigger than 0? I mean, obviously you could plug in x equals 1,000 and figure out what number it is, but you don't. That seems like a lot of work. You don't actually need to know what the number is. You just need to know when you plug in x equals 1,000, is the result a positive number or a negative number? So I can just do that by thinking informally. If I plug in x equals 1,000, 1,000 minus 1 is a positive number. And I'm going to be multiplying that by 1,000 minus 2, which is also a positive number. And I'm going to be multiplying that by 4 minus 1,000. Well, 4 minus 1,000 is a negative number. So positive times negative equals a negative number. And so I know that the answer here is false. It's not positive. And I don't even know what number you get when you plug in x equals 1,000, but I don't need to. I just needed to figure out, is each term positive or negative? So then if I want to know what's the limit as x approaches infinity, well, I know that when f equals 1,000, I'm getting a negative number. Here I'm asking what happens when x is even bigger. If you think about it graphically, here, let's write it this way instead. So we've got the roots for this function are 1 and 2 and 4. We already looked at what happens when you plug in x equals 1,000. We've got, when x equals 1,000, you've got a positive value times a positive value times a negative value, which means that the overall output is negative at x equals 1,000. The point that I want to bring out here is this same pattern of positives multiplied by negatives, this pattern would happen no matter what the x value was, as long as it's larger than x equals 4. Think about why that is for a second. If I have any number that's larger than 4, this is always going to be positive. This is always going to be positive. And then as long as x is bigger than 4, 4 minus a number bigger than 4 is always going to be negative. So this pattern doesn't just apply to x equals 1,000. It applies to all the x values in this entire interval. And what that means is the output of my function in this whole interval where x is larger than 4 are going to be negative. So that's the big idea I wanted to bring out here is if you want to know what the behavior of your function is between the roots, all you have to do is think about the pattern of positives multiplied by negatives, and whatever pattern you get when you plug in one of those values, that same pattern applies to all the values in the interval. Check it out. X equals 3. What do we get? We get 3 minus 1 is positive. 3 minus 2, positive. 4 minus 3, aha, now that's positive. So the only difference between this interval and this interval, these first two are the same. It's that this last term, the 4 minus x, has gone from being positive to being negative. And it sort of makes sense, right? If x equals 3, this is positive. As x gets larger and larger and larger, eventually x equals 4. What happens when x equals 4 exactly? When x equals 4 exactly, we've got positive times 0. So right exactly on this x value equals to 4, you've got positive, 0. And so that's why your curve has hit the root. And then once you cross x equals 4, now you've got positive, negative. And so now when you multiply those, you get into the negative region. So what we know is between x equals 2 and x equals 4, all of these values are positive. We know that eventually you've got to kind of turn around here because we have to head back towards 0, because when you plug in x equals 2, we've got 0 again. So you're going to end up having this kind of alternating pattern like this. And again, what I wanted to emphasize is the pattern in the region applies to all x values in the region. So here we'd have, let's see, x minus 1 shouldn't have changed. X minus 2 is the value that changed from here to here. So I know that's going to be negative, and that's going to be positive. So again, like each time you cross a root, it's the term, the term that involves that root is the one that's changing signs. So this idea is important in calculus. In calculus, you call these critical values. For right now, I'm going to define critical values this way. For whatever function you have, its critical values are the x values where the function might change from being positive to negative or negative to positive. And I say might change. I don't mean the places where it actually does change. I mean places where it's possible that it would change. You'll see more in a don't sweat this definition too much right now. It's not the best definition. We're going to see a better one in a minute. Actually, let's do a new video right now.